Let's define what is meant by a Cauchy sequence. A sequence of real or complex numbers is called a Cauchy sequence if and only if, for epsilon greater than 0, there exists a positive integer n such that whenever n and m is greater than or equal to capital N, we have the absolute value of an minus am is less than epsilon. This means that if I go sufficiently far down the sequence, more precisely beyond capital N, then any two terms, an and am, are arbitrarily close. Note that m and n are arbitrary, and we are free to choose any positive integer for n and m as long as they are greater than or equal to capital N. Cauchy sequences are a special kind of sequences which converge, but the limit is not necessarily known. We will prove this fact later in the video. Let's prove this lemma, which states that if a sequence an is Cauchy, then it is bounded. We pick epsilon to be equal to 1. Then there exists a capital N, a positive integer, such that whenever n and m is greater than or equal to capital N, we have that the absolute value of an minus am is less than 1. In particular, if we take m equals capital N, then little n is greater than or equal to capital N implies that the absolute value of an is less than 1 plus the absolute value of a capital N. So, the absolute value of an has to be less than or equal to the maximum of these values, the absolute value of a1, the absolute value of a2, up to the absolute value of an minus 1, and also 1 plus the absolute value of a capital N. This has to be true for all natural numbers n, which completes the proof. Now we are ready to show that an is a convergent sequence if and only if an is a Cauchy sequence. Let's first show that if a sequence converges, then it must be Cauchy. We fix any epsilon to be greater than 0. Since an converges to a, there exists a capital N and positive integer such that little n is greater than or equal to capital N implies that the absolute value of an minus a is less than half of epsilon. If we replace n by m, we have that m is greater than or equal to capital N implies that the absolute value of am minus a has to be less than half of epsilon. Now, whenever m and n are greater than or equal to capital N, we have the absolute value of am minus an is less than or equal to the absolute value of am minus a plus the absolute value of an minus a. This is less than half of epsilon plus half of epsilon, which equals epsilon. Conversely, we have to show that if a sequence is Cauchy, it must be convergent. For this purpose, we need a candidate for the limit a. We will produce an auxiliary sequence which is monotonic and bounded. Then we know from a previous theorem that such a sequence must converge. We let Bn to be the supremum of the set ai, where I is greater than or equal to n. Notice that using the previous lemma, because an is bounded, the supremum of an exists. So Bn is well defined and also bounded. To prove that Bn is monotonically decreasing, we know that Bn is the least upper bound for the set ai where I is greater than or equal to n, so by definition it is an upper bound for the set. Hence it is also an upper bound for the subset ai where I is greater than or equal to n plus 1. Since Bn plus 1 is the least upper bound for the set ai where I is greater than or equal to n plus 1, we must have that Bn plus 1 is less than or equal to Bn. This means that Bn is monotonically decreasing. Now we have shown that Bn is bounded and monotonically decreasing, so it must converge to a limit a, which is actually the infimum of the set Bn, where n is a positive integer. Now we fix any epsilon greater than 0. Then there exists a capital N, a positive integer, such that whenever n and m is greater than or equal to capital N, we have that the absolute value of an minus am is less than half of epsilon. This means that an minus half of epsilon is less than am, which is less than an plus half of epsilon. Now we take the supremum over all m which is greater than or equal to I, and also greater than or equal to n. Since each am is greater than an minus half of epsilon, we know that the supremum of am over all m greater than or equal to I is also greater than an minus half of epsilon. On the other hand, an plus half of epsilon is an upper bound for the set am, where m is greater than or equal to I is greater than or equal to capital N. So, the least upper bound should be less than or equal to this number. Now we know this supremum is the definition of Bi. So this means that an minus half of epsilon is less than Bi, which is less than or equal to an plus half of epsilon. Now we take the infimum over all I, which is greater than or equal to capital N. Notice an minus half of epsilon is a lower bound for the set Bi, where I is greater than or equal to capital N. So the infimum of Bi, where I is greater than or equal to capital N, is greater than or equal to an minus half of epsilon. On the right hand side, Bi is less than or equal to an plus half of epsilon, and this stays the same for the infimum. Since Bn is monotonically decreasing, the infimum of the set Bi, where I is greater than or equal to n, is equal to the infimum of Bi, where I is a positive integer. This equals a. In other words, an minus half of epsilon is less than or equal to a, is less than or equal to an plus half of epsilon. So for all n greater than or equal to capital N, we know that the absolute value of an minus a is less than or equal to half of epsilon, which is less than epsilon, and this completes the proof. As an example, let's show that the sequence an, defined as 1 plus 1 over 2 plus 1 over 3 plus up to 1 over n, is divergent using the previous result. It suffices to show that an is not Cauchy. We pick epsilon to be 1/2 and any capital N, which is a positive integer. We set n to be equal to capital N and m equals 2 times capital N. Then the absolute value of an minus am is equal to 1 over n plus 1 plus 1 over n plus 2 plus up to 1 over 2n. Since each fraction is greater than or equal to 1 over 2n, and there are n fractions in total, the sum is greater than or equal to n times 1 over 2n. This equals 1/2, which equals epsilon. Hence, we have shown that for a certain value of epsilon, no matter what positive integer n you give me, we can find values of n and m such that the absolute value of an minus am is not less than epsilon. And this completes the proof.